Alright, for the pre-lecture for today, we're going to be talking about entropy. This is chapter 2 of the textbook. So in the textbook, I think section 2.1 is a kind of nice introduction to this, so that's worth reading through. Section 2.2, if you want to, you can read through that if you find that helpful. I think it's sort of confusing how it's written, so I don't think that that's the best source for this. I posted another source with the pre-lecture notes, so you can see if that's more clear to you, but they do use slightly different notation than we use. They use p of x, little p of x. That means the probability that the random variable x equals the value x. So watch out for that in that source. Starting with uncertainty, the idea here is that a fair coin has more uncertainty than a coin that comes up heads 3/4 of the time, because we can be pretty sure that the second coin will come up heads. Whereas with a fair coin, we really don't have a good guess of what that's going to come up, since both possibilities are equally likely. There's a lot of uncertainty there. If one of the possibilities is more likely, then we have some idea of what's going to happen, so there's less uncertainty there. So where we have more uniform probabilities, where like a bunch of different possibilities are equally likely or close to equally likely, that means the outcome is going to be more uncertain. Whereas if it's like really heavily skewed, where one thing is much more likely than everything else, that's going to be less uncertain. And then for information, we say that a relatively unlikely event carries more information than a likely event. So this probably seems a little strange, but this makes sense because if we know the sum of two die rolls is 2, so this has a probability of 1/36, we know that they are 1 and 1, because that's the only outcome where that event happens. Whereas if we know that the sum of two die rolls is 7, and that outcome, or that value has probability 1/6, then the rules could be 1/6, 2, 5, 3, 4, 4, 3, 5, 2, or 6, 1. So knowing that the sum of the two die rolls is 2 carries more information than knowing the sum of the die rolls is 7. So this is why we have this idea that unlikely events carry more information, because then we can narrow down what's happening more. Whereas if a likely event happens, then it's sort of like there are all these different possibilities and we don't know which one it's going to be. For entropy, entropy gives us a measure of the uncertainty of a random variable. It's defined by this formula. So we denote it h of x, and then take minus the sum over all possible values x of the random variable x, and the things that we are adding up are the probability that big X equals little x times log base 2 of the probability that big X equals little x. And the units for entropy are bits. So all of our outputs are going to have the unit, or all of our results for this h of x are going to have the unit bits, as long as I remember to write it, which I might forget. So let's look at an example of computing entropies for some random variables. So let's flip a fair coin once, so x is the number of heads here, so it might seem like kind of a silly random variable, but we'll look at it here. So the possible values for this one are 0 and 1. There can be 0 or 1 heads in a single coin flip. So then when we're looking at h of x, we're going to look at those probabilities, or those possible values, and look at their probabilities. So when we're looking at x equals 0, the probability that we have 0 heads, that happens if we flip tails, so that is probability 1/2. So we've got 1/2 log base 2 of 1/2. and then plus, now we look at where big X equals 1, and that is when we've got 1 heads, so that has probability 1/2. So we've got 1/2 log base 2 of 1/2. So remembering our logarithms, we've got minus 1/2 minus 1/2, so this works out to be an entropy of 1 bit there. Now if we flip a coin with probability of heads 3/4, X is the number of heads again, but now the probabilities are different. So our values are still going to be 0 or 1, but now their probabilities are different, so looking at when X equals 0, now if heads has probability 3/4, then getting 0 heads, that has probability 1/4, so we've got 1/4 log base 2 of 1/4 plus, and then for the probability, we're looking at when X equals 1, that's going to be when we get 1 head, so that has probability 3/4, so we've got 3/4 log base 2 of 3/4. So if you work this out, this comes out to about 0.81128 bits. So we can see that the entropy for this random variable is smaller than the entropy for the first example that we did, which is consistent with what we said about uncertainty for a fair coin versus a weighted coin. So we've got more entropy when the probabilities of the outcomes are more uniform, or in this case, when they're equal. So now let's look at a slightly more interesting example where we flip a fair coin twice, and X is once again the number of heads. So our possible values here are 0, 1, and 2. So we can have 0, 1, or 2 heads in 2 coin flips. So now figuring out our entropy, we've got minus, now looking first at X equals 0. So that means we've got tails, which happens with probability 1/4. So we've got 1/4 log base 2 of 1/4. Now looking at when X equals 1, well, the ways that can happen is heads, tails, or tails, heads. So that is probability 1/2. We've got 1/2 log base 2 of 1/2. And then finally for X equals 2, that means we've got heads, so that is probability 1/4. We've got 1/4 log base 2 of 1/4. So working that out, this is going to come out to 3/2 bits. So notice that the values of the random variable X, what the outputs are, doesn't actually matter for the entropy, it's just the different probabilities. So all that matters for this is the probability that each value occurs, and sort of how equal or unequal those probabilities are. So this formula might seem kind of strange or unnatural or like it's coming from nowhere. It actually turns out that for the kinds of properties that we want to be true for entropy, that this is the only way that it can be defined. So that's something that's covered in the book. You can take a look at that if you want. It's a pretty cool result, but for our purposes, knowing what entropy means and knowing how to compute it, that should suffice. Alright, so now we're going to talk about another type of entropy, which is joint entropy. So here we're going to consider the entropy of 2 variables together. So if we've got 2 random variables, X and Y, and we're looking at their joint entropy, we compute this by looking at all possible pairs of values of X and Y. So looking at combinations of this output for X and this output for Y. What's the probability that those two happen together? find that probability, so the probability that x equals xi and y equals yj, and add up those probability log base 2 probability, and then do negative. For looking at an example for this, if we're flipping a fair coin once and x is the number of heads and y is the number of tails, then the possible pairs for values would be 0, 0, 1, 0, 0, 1, and 1, 1. And the probabilities that each of these occurs, so if we've got 0 heads and 0 tails in a single coin flip, that's going to have probability 0 because that's impossible. If we've got 1 heads and 0 tails, that has probability 1/2. That happens if we flip heads. If we've got 0 heads and 1 tails, that happens if we flip tails, so that is probability 1/2. Getting 1 heads and 1 tails, that's impossible, so that is probability 0. So we can add up minus, then over each pair, we're doing probability log base 2 probability. So we've got 0 times log base 2 of 0 plus 1/2 log base 2 of 1/2 plus 1/2 log base 2 of 1/2 plus 0 log base 2 of 0. And of course you can leave out those probability 0 terms if you want because they're just contributing 0. So this works out to be 1. And if you remember the entropy of x from an earlier example, that was 1. And since y is essentially the same in terms of the probabilities, we also get that has an entropy of 1. So notice that here these variables are really related to each other, and we see that the joint entropy is the same as the individual entropies. So that's not a coincidence that that's happening. Now let's look at another example where if we roll a die twice and x is the result of the first roll and y is the result of the second roll, then our possible values are going to be 1, 1, 1, 2, 1, 3, 1, 4, etc. All of the possible pairs 1 through 6. So there are going to be 36 of those. Now, when we figure out the entropy, each of these has probability 1 over 36. So we're going to do negative and then add up the probability 1 over 36 times log base 2 of 1 over 36 plus 1 over 36 log base 2 1 over 36 plus, and then continuing like this, so there are going to be 36 of those, so you can see why I don't actually want to write them out. And then this will work out to be minus log base 2 of 1 over 36, since there were 36 of those, and this is log base 2 of 36, which is about 5.1699. If you work out what the entropy of x and the entropy of y are, so that's a good exercise that I definitely recommend. They turn out to be log base 2 of 6 and log base 2 of 6, and those are 2.5850. Oh yes, and these are bits. See, I knew I was going to forget bits. Everything is bits. So notice for the second example here that when we add together the entropies of x and y, we actually get the joint entropy of x and y here. And in this situation, the variables x and y are actually independent because the first roll and the second roll aren't going to have any impact on each other's probabilities. So this is true in general, that we have the entropy of x plus y is less than or equal to the entropy of x plus the entropy of y. And these are actually equal if and only if x and y are independent. So for independent variables, you can figure out the joint entropy by figuring out the individual entropies and adding them together. Another type of entropy that we can look at is conditional entropy. So the conditional entropy of x given y gives the uncertainty or entropy remaining in x once y is known. So we can compute that by doing the joint entropy minus the entropy of y. There's another way to compute it in the book. That's kind of a pain. This should serve nicely for us, so we'll mostly stick with this. If you're interested in that other way to compute this, feel free to take a look at that. And then it's also true that if x and y are independent, that the entropy of x given y is equal to the entropy of x. So if y is known, that doesn't give us any more information about x, so x still has the same entropy or uncertainty that it did originally without knowing y. So that's true for independent variables there. So that's the video on entropy. So make sure you answer those pre-lecture questions, and we'll do a quick review of this at the beginning of class on Friday, and then into the group work and finish with going over some solutions to group work.